Afternoon, everyone. Thanks for making time here. Today we continue with superposition, the second half. Okay, this part is a bit more jumbled up because there's multiple things. There's one big category, one category, right, which is single slit and Rayleigh criterion. They are based on like the same kind of thinking. Then there's the second half, standing wave. Okay, so today, right, the style will be slightly different because I didn't manage to come up with as many weird questions to ask like the last time, so I didn't do it in the same way. Instead, right, I compiled some of the things that are helpful to allow you to visualize this phenomenon better and also derive the equations. So yeah, we'll do it in terms of PPT. Let's begin. Anytime, right, you have questions to ask, right, just feel free, okay? Diffraction, if we recall, is a spreading or bending of wave. What does it mean by geometric shadow? It means, right, that there will be some portion, right, some zone that by right, there shouldn't be anything there, okay? For example, wave is coming this way. It should just go straight through, right? And let's say here got a gap, right? So by right, nothing should be here and nothing should be here. But we do see that the wave actually will enter those region. That's because of the bending, yeah. So this is actually quite counterintuitive in the sense, right, that if you were not educated in wave before, and you look at this situation, right, something going into a hole, it should just be preserving, right, its original direction and go through. The part that cannot go through, right, I mean the part that's blocked by the obstacle, just get blocked out. The part that can go through, it just go straight through in the same way. But why is it that they will actually spread out? That's actually something that's strange about this wave behavior. So as to how to draw it, right, this diagram will show you, okay? So you can see from this diagram, right, that the bigger the aperture, okay, the less the degree of the spreading, okay? And then how you actually draw it, right, you need to make reference to the aperture size. So you see the very faint dotted blue line there, right, showing you that that's the size of the aperture. So it's near the boundary of the aperture, right, that you'll see this bending occur. Yeah, so in the middle portion, you just draw straight lines, and near the boundary, you draw the curve. Then you draw a straight line, right, that like slopes up and slopes down to guide your spreading. Yeah, in fact, you should draw it here and draw it here, okay, to guide your drawing of the curve part. And when the aperture is really small, then, right, there's very little of the straight part, okay, in fact, it's almost non-existent. Then you'll become, right, the whole thing would be just very curved. Yeah. What does diffraction do to the wave? One thing is, right, it will not alter the wavelength. So the wave will remain the same, just, right, the direction of propagation will change. Yeah. In what situation will we experience diffraction and its effect? The last lesson, right, on double slit, we already saw, right, a certain diagram that there seems to be some envelope, right, preventing the intensity of the fringes to be like as high as it should be, okay, and that's actually, right, due to diffraction. And of course, right, the fact that when your mom is in the kitchen, she yell at you, you're in the living room, okay, and separated by a wall, right, yet you can hear her loud and clear, right, it's a diffraction of sound wave. Yeah, so diffraction is actually almost everywhere. And we look at where we are seated. Maybe, I don't know whether you turn on your room lights or not, that you see shadows, right, and shadows are seldom like straight cut at the boundary. There's always, right, fuzziness at the edge. That's also effects of diffraction. Now, right, let's go straight to single slit diffraction. Single slit diffraction, right, is a very strange phenomenon. Why? Besides, right, just the spreading of wave that we expect, right, from this previous diagram, it's actually telling us, right, more details. We see that, right, in a single slit, obviously, right, you expect two things. Okay, let's say, right, before you know that there's this phenomenon, when you have a wide slit, right, you actually expect, right, the size of the dot, okay, that you see, right, on the screen should be big, right? Because, right, it's like a big aperture. So the image that you see at the other side should just be a bigger bright spot. If you have a narrow aperture, you should just have a narrower bright spot. Turns out, right, that you have actually opposite effect. Okay, the wider slit give you a narrower bright spot, and the narrow slit give you a wider bright spot. That's number one. Then number two, right, you actually should just expect, right, okay, we know that they spread, so we should just get a bright spot that tapers out, right, in brightness. But it turns out, right, that that's not just it. There are also, right, regions that light simply don't fall. Okay, it's like forbidden. And then after the forbidden region, you see another region, right, that the light is allowed to fall, and then another forbidden zone, so on and so forth. So this phenomenon is also strange because, right, we should just expect light to just go through, right? How come it go through already, right? It can still decide where to go, where not to go, yeah. But we know the logic of such things, right, from the previous section, which is this is the effects of interference, yeah. Because when you have two slit, you can have waves from one slit and waves from the other slit arriving at the same point. They can undergo constructive or destructive interference, and therefore, right, give you bright dark fringes. They simply mean, right, certain zone cannot fall, certain zone can fall into it. Okay, but now, right, when you have single slit, isn't it strange that there seems to be some form of interference effect happening? Yeah, because without interference, right, how come there will be some regions that light is not allowed to be present? And if you're thinking about this angle, right, you're on the right track already, because, right, single slit diffraction is also an interference effect. Yep, so let's look at the diagram again. And we just have this formula given to us first. Okay, we'll make sense of it later on. So for single slit diffraction, right, the formula that we use, right, is always relating the angular position of theta of the minima. Okay, for single slit diffraction, we don't do maxima, we do minima. We want to know, right, where light is not supposed to fall. Later on, you'll appreciate it better. Then what is this formula is like similar to your diffraction grating one, right? But the left-hand side, right, this term is not the same anymore. For diffraction grating or double slit, right, you're talking about the gap between slits, right? Okay, from here to here. So that's your D. Here, right, we are talking about size of the slit, which is A. Okay, so referring to different things. Take note. Okay, there's this idea that you need to be familiar with before we can proceed to prove, which is the Huygens principle. Okay, this one is talking about how, right, when you have a particular wave fronts, right, you can think about the wave front as being made up of many smaller wave fronts. Okay, and also containing many smaller wave, creating wave forward and forming the next wave front. So you see, you just think about the first purple line on the left is like one particular wave front. Every point on the wave front, right, could be a source or can be thought of as a source. Then they are emitting waves spherically, right, because they are all point sources. So the part, right, let's say this portion here and this portion here, right, the effect actually is one emitting down, two emitting up, right? When they meet, right, they will all cancel out. Yeah. Where they will not cancel out is the direction that's forward. Okay, so turns out, right, that when you draw a series of these semicircle arc, the part that which are in between them all will cancel out, forming, right, the resultant of a straight line, okay, like this. Okay, so this becomes the next wavefront, and so on and so forth. So every wavefront can be thought of as more sources forming the next wavefront. Yeah, so that's how you visualize this. So if we imagine, right, the single slit as made out of many sources, right, then we can actually start to ask the question, right, what are the conditions for these sources to constructively or destructively interfere with each other at some given point? Okay, that's somewhere outside, maybe somewhere here. Okay, so let's dive deep. Suppose, right, we have a particular point here on the screen. Okay, that's at an angular position of theta. Yeah. So what do we think, right, is the condition for them to arrive, right, such that they will destructively interfere and lead to a minima? We ask, what is the condition for minima? Minima means, right, must have destructive interference, right, and that means the wave must arrive in antiphase. Then wave phase difference, right, contributed by two sources. One is the source themselves, and one is the path difference. So if we consider, right, the single slit as made out of many sources, right, they are supposed to be in phase because, right, they lie on the same wavefront. Yeah, so they are in phase. Then, right, since they are in phase, the only thing that can cause phase difference, right, when waves from those points that we are comparing arrive somewhere else, will be the path difference. So let's consider, right, wave from the bottommost little source, okay, and the one that's in the middle. Yeah, and these two sources, right, are half a slit separation, a slit opening, slit size apart. Okay, half a slit size apart. Then, right, for them to disruptively interfere, their path difference will be one possible location will be one possible value will be half lambda. Okay, if that's the case, then you can write this equation. Sine theta will be half lambda divided by half a. Yeah, so there you have it. A sine theta 1 equals to lambda. But then, right, these two lines, right, are just talking about wave coming from these two sources. Okay, what about all the other points? Well, if, right, the first point and the point in the middle can fulfill that condition, then, right, by symmetry and just by pushing the whole diagram up a little bit, right, second point and the second point from the middle will fulfill the same condition as well. And third point, fourth point, and every point. So it turns out, right, that as long as we fulfill this condition, right, all of the bottom half and all of the top half, right, will destructively interfere with each other. So the bottom half, right, looks like it's like one giant source like that. They will always find someone on the top half at loggerhead. Okay, they have a path difference of half lambda with someone else in the other half. So they will cancel out each other. So the net result, right, is that when the wave arrives there, right, you have zero intensity. Yeah, because all the tiny waves contribution, right, from the bottom half and top half cancel each other. So you can play them as like two teams, or team A and team B. Okay, that accounts for first minima. How do we get second minima? Well, let's consider, right, that we split the slit into two slit again, two slit. Then within each half of the slit, right, we split it into half again. So within half of the slit, right, you have the blue one cancel out the red one. The other half, same thing happen. Yeah. And if that happens, right, at a particular angle theta, then, right, you write out the equation. See, now it's what is the this size here, okay? This amount here, right, will be A upon 4. Just now it was A upon 2, now it's A upon 4. You write into the formula. Now you turn out to have a new equation, right? A sine theta, left-hand side the same. Right-hand side, you have a 2, okay? Because now we are making the slit like half the size. So this is telling us, right, what is the condition for the second minima. Okay. Similarly, right, you want to find the third minima, what you do, cut the slit into 3. Then each half or each third split into 2 more halves. They fight each other, disruptively interfere at some angle. Okay. Then you have the third equation, and so on and so forth. Okay. Yep. So with that, right, you have the formula already. Okay. This exercise, right, if you find that whatever I said just now confusing, right, later on you take the PDF file, look through it again. Okay, you'll get it one. And once you get it right, you'll understand exactly why so already. You won't come back and say, oh, why the formula all like same but different and very confusing. Or people will find them confusing because they don't understand what's the underlying mechanism. Yeah. So we always want to seek understanding and mastery. Okay, I want to say in this slide. So just a recap. Okay, minima, right, always occur at A sine theta equals to n lambda. Now, right, let's revisit the double slit pattern. You see, we compare it with the single slit pattern. So suppose, right, we have a single slit of a certain size, A, okay, slit size A. Then you have a double slit. Each of the slit, right, have the same slit size, okay, as before. Turns out, right, that you see some similarity in the pattern, okay. The single slit, right, pattern is given by this intensity graph, okay. And that seems to turn into an envelope for the pattern for the diffraction, sorry, double slit pattern. Why so? Think about it this way. Light from a single slit alone, right, has a certain underlying mechanism directing where the light could land, where the light couldn't land. Okay, just one slit alone. Suppose nearby now there's another slit. So now, right, there is some positions that light from the other slit could land and some positions could not land. Therefore, right, combined together, those positions that light couldn't land, right, or is it, and it's not just could land or could not land. There is also a rule saying, right, what is the likely intensity. Therefore, at those positions, right, whereby intensity is high, then the double slit interference effect, right, will be subjected to the base level of intensity due to the individual slit. Because if light can land there, and now you have two sources landing there, then you do your interference between these two sources. Then you come up with the double slit pattern, the fringes. Yeah, and therefore, right, the single slit pattern, right, will set the upper limit for how much the intensity of the double slit fringes will be. Okay, so you see this phenomenon here, and there will be some unfortunate double slit fringes, right, that fall right at where the minima are. Okay, for example here. So these fringes, right, would not appear because, right, due to the diffraction effect from the single slit, right, there's not supposed to be light there. Therefore, right, light didn't even fall there. Okay, so how would there be double slit interference taking place in the first place? Yeah, so that is a logic. And problems of single slit diffraction, right, sometimes are coupled with double slit. Okay, and the pattern of the question is always, right, ask you to find what is the order of the missing slit. Yeah, I think we have an example later on. We can take a look. So once again, right, this is the diagram now bigger. Okay, so see these are the missing order. So you can count all this 0, center one is 0. Okay, so this 1, 2, 3, 4, 5, 6. So here, right, order 7 is like missing. Sometimes it may not be exactly 7. It could be, or I think it's order 8. Oh, maybe here got one more. Order 8 that's missing. Oh, it's amazingly difficult to write 8 with my mouse. Okay, you can't tell what's that, right? That's an 8. Yep, so that's the thing that I'm referring about, okay, the missing order. Yeah, so this example, right, you can go and try, okay. You will aim to use those two equations, A sine theta okay, equals to lambda. I'm referring to the third part of this question, okay. You see, they're asking how many bright fringes, right, are contained within a central bright band. So we are talking about this one. So we want to find, right, what is the location of this first minima, okay. So we use this to do that, okay. A sine theta equals to n lambda. A sine theta equals to lambda. So lambda here is actually 1, okay, because we're talking about first minima. At the same time, right, you will use the formula, right, d sine theta equal n lambda. You may ask, right, aren't we talking about a double slit? Why you use this formula? Normally, double slit you use y equals to n lambda L over d. But here, right, we are talking about angular position. Yeah, it's implied on angular position. So it's not so important, right, to know where is it on the screen. But you should know what is important, right, is what is the angle from the principal axis. Okay, so we want to match these two theta. Want to equate these two theta, i.e., right, want to equate the two sine theta. So you will have, right, lambda upon A equals to n lambda upon D. Okay, so see the lambda will cancel out. So n is simply equals to D upon A. So that tells you, right, which order of the double slit pattern, right, is having the same angular position as the minima. Okay, so that is the one you can't see. So after you found the n, right, let's just suppose that it's let's say 10. Okay, so the 10th order is missing. So how many order can you see? You see 1 up to 9, yeah. Then you have to consider on the other side also 1 to 9, so 18. Then you still have to consider 0th order, so 19. Okay, so that's an example of how you go about determining how many bright fringes are within the central bright band. Okay, let's continue. Once again, right, this is the whole setup in case, right, you're always wondering where do we get this kind of diagram from. Okay, it's a laser, single slit and a screen. Yeah, and this like magnified of the screen. And always do in a dark room, then you can get this kind of image. This one we've seen in the previous handout also. And you can notice, right, that with a larger wavelength, which is red, okay, you have a larger, wider band, okay. See, here is like wider compared to here. Yeah, because A sine theta equals to lambda. Here yet another diagram showing you, right, that this single slit envelope, right, applies not just for double slit, applies for everything. Okay, even diffraction grating. Yeah, diffraction grating, you also see your envelope. Okay, with that, right, we can move on already. Okay, we can move on to something related to single slit, okay, which is Rayleigh criterion. You were bound to have this kind of experience before. For example, right, you see a car, the headlight, right? The headlight are equally, I mean, the spacing between the two headlight, right, remains constant. Yeah. But when the car, right, move further and further away from you, right, you can't tell, right, that there are two headlights anymore. Yeah. You see that they appear to be just like one. So why is there this phenomenon? Yeah. Similarly, right, why is it that when you are sitting further and further away from the whiteboard, let's say your teacher draw write any word, okay, at some point, right, let's say you write a small letter A, okay, at some point, right, you will fail to see the what that letter is about or draw anything. You can't tell. Why is it that you can't tell? We know, right, by intuition, is because, right, the two things, right, seem to be closer and closer together. Or let's say if your teacher draw two dots on the whiteboard, right, quite close, but you could tell when it's nearby, when you are seated nearby. But when you're far away, right, you couldn't tell that there are two dots already. And most will just see that they look like one smudge, okay? And that is, you see, we know by intuition that when things are too close, then, right, we can't tell them apart. But yet, right, in both examples that I just said to you, right, the distance between the two objects, right, whether it's two headlight or two dots that your teacher write on the blackboard, okay, they have the same gap, okay. The gap between them didn't change, but yet, right, when you are further and further, you can't tell them apart. So what is it that is becoming smaller? The answer is actually, right, their angular position, okay, with respect to your eye, the angle between these two things with respect to your eye, or with respect to anything, right, that's trying to make the observation. So that brings us to Rayleigh criterion. Rayleigh criterion, right, is the study of the condition, okay, which allow us to distinguish two things apart from one another. Let's start off, right, by looking at this scenario whereby we have two sources, okay. So you see, first source, right, let's say these are sources of light, okay, sources of light. And here got a slit. So first source, right, the source on the left is 1. You will make an image on the screen. So this belongs to 1. Then the other one will make another image on the screen. That's 2. If 1 and 2, right, this angle is far apart, okay, then we could tell that these two are different things, okay. But yet, right, you also need to realize that because it's a very narrow slit, so there's also, right, single slit diffraction effect. So belonging to each of the 1 and 2, right, the spot got the intensity pattern, right, that is the single slit diffraction pattern. Yeah, so got minimal one. If now, right, you now if you bring the two sources, right, nearer to each other, yeah, what will happen? Now, right, you see that these two sources, right, will start to smudge together. And reason behind it, these two diffraction envelope, right, belonging to the two sources will start to smudge together, overlap too much already. You see, how could you tell that there are multiple things? If you draw an intensity against position graph, right, so y-axis is the intensity, you could tell things, right, when they were like the intensity graph is that far apart. Yeah, because, right, there's enough contrast. So from here to here, right, there's a huge contrast. Yeah, so it's went from bright to a dark region, then another bright region. So you could tell that they belong to different things. But when the bright parts, right, are all too close, then, right, the in between, it may dip a little bit, but not enough dip, right, to show you that there is a difference in the intensity. Then you couldn't tell. Okay, for example, this graph is showing you, right, in detail what we are trying to say just now. So see, if these two graphs, right, the two green color one are too close, Then right, here sum up right will be in fact even higher. So you just see right one entire long smudge belonging to the corresponding to the red graph. Okay. So what is the limit right that allow us to tell? The limit right is as such. If right the let's look at the next diagram. Okay, this diagram is clearer. If right the angle between them is just nice right equal to the first order minima of either of the sources, and we must have the sources same lambda lah, okay, same lambda, then this equation is easier to work out. Okay, then right, see if the two sources right, the angular separation is equals to the first order minima, which is like the separation is like here. Okay, then the angle on the other side right is also the same. Hang on, my mouse not working too well. Yeah, so the angle here is the same, and if it's equals to the first order minima for single slit, that means right, the position of image 2's central maxima right will just nice coincide with the first order minima of image 1, and that will be right the closest they can be. Okay, further than that is fine, smaller than that cannot. Okay, so that is a condition for two images to be resolved, and hence right the angular separation that can exist right will be given by this formula, and this is the minimum theta. Usually right we expect this theta to be really small. Okay, why small? Because you can look at the a sine theta equals to lambda formula. So from that formula right, the single slit diffraction formula, you could tell right for any a that is significantly larger than lambda, theta will be very small. Okay, because the a is much larger than lambda, so theta will be very small. And why is a much larger than lambda? That's just the construct of things. Okay, could you have a that is very close to lambda? Sure, by all means. Okay, but usually that's not the case. Hence, right, you can perform a small angle approximation if theta is indeed very small. So theta minimum will be equals to lambda upon a. Okay, so this will be the Rayleigh criterion. Actually, both forms are okay, but this will be the simplified one for small theta. Circular aperture is slightly different. Okay, what is the difference between rectangular and circular aperture? One right is this shape, one is this shape. Okay, or it's a dumb clarification, right? You rectangular versus circular. Okay, the Rayleigh criterion is slightly different. It contains 1.22. Obviously, right, this is a product of some more complicated manipulation. It's not as straightforward as whatever we derive for the rectangular slit. Rectangular slit one is simply the formula for single slit diffraction. Circular one is need to do extra work. Yeah, so suppose right, we go back to the problem we started off with. We ask ourselves this question. Headlight right is 1.5 meter apart, so this one is fixed one. Okay, so how far right must the car be? You see, you know right that if the car is 10 meter away from you, the angular separation right between the two headlight to your eye, or just open one eye, don't open both eye. Okay, open one eye and you see. Then right, the angular separation will be quite big. and they are far apart. So you could tell them as two different objects. As the car get further and further, right, still 1.5 meter, but the distance between them become, between you and the car become further and further. So the angle becomes smaller and smaller. So what's the limit, okay, for you to still see them? We already know, right, that the limit must be lambda over A. That's just using the formula, okay? And the single slit in this case, right, is your eye, yeah, 3 mm, or the pupil size, 3 mm. Our pupil is what? Pupil is the part of the eye, right, that lets the lights in, okay? Yeah, you know, when you go from a dark room to a bright room, right? And if someone look at your pupil will look very dilated, or you open up. Because when you are in a dark room, right, your biology will sense the darkness. So you open up the pupil, right, to allow more light in. So if you suddenly walk out into the room, into a bright room, right, then you feel, wow, suddenly feel so bright. And someone, if they observe your pupil also dilated. When you excited, your pupil will also get dilated, by the way. If you see your dream girl, okay, sitting next to you, confirm your pupil will be dilated, okay. If my JC crush, right, appear in front of me, right, my pupil will become the size of my eye. Okay, this is the, what did I say just now? Okay, lambda over A. So you plug in the wavelength of light and the pupil size, you get this minimal angular separation, which is the Rayleigh criterion. Second step, right? Then you do the same thing, right? Okay, actually you don't need to tangent. You can simply just put theta. This theta is also equals to 1.5 meter divided by the distance. Okay, you see here are two headlight are here and here, right? 1.5 meter, and you are very far apart already. Yeah. So this angle is much bigger than it should be. It should be very, very small. So this is your theta minimum. So you just take the 1.5 meter divided by this x. Okay, that will give you theta. Or rather, that will be equal to theta, and you solve for the unknown x. Some of you may be very uncomfortable by now, right? How we can use this theta right away without even using tangent. Because, right, for small angle approximation, tangent theta equals to sine theta equals to theta, or for theta equals to for theta in radian. So since here you already solve in radian, and how you know it's in radian, not in degree, confirm one, because whenever you solve this kind of thing, right, okay, in a ratio form, it's actually, right, using the radian version of things already. It's no longer using degree. So here you can just use the formula and equal to theta, no need to tangent. And here don't need to write this line. Yeah, I don't know why my answer had this. Because, right, already know that this is a small angle. Okay. Next portion. Now that we know what is resolution, right, and what is the condition to resolve things, right, the next idea that come in is how do we quantify how good something is, right, in resolving objects. So simply, right, we are using the theta minimum as the thing, right, to quantify, okay, resolving power. Resolving power means what? Means how finely can you see? Okay, how finely can you see? How sharp can you see? Yeah, and you look at this formula, right? You see, if you want the resolving power or this theta to be small, what can you do? Where did the arrow go to? Okay, sorry, the sequence messed up. How can you get the theta minimum, right, to be small? You can do it by two ways. You can make the lambda small, or you can make the b larger. Okay. That is like just looking at the formula. How do we, right, go about achieving that. But you see, for visible light, right, there's actually a limit. This one can't be much smaller. Why that? Because visible light is just 400 to 700 nanometer. If you want lambda to be small, use blue light lah. But then blue light is also not much better than the red light. Okay, so it's the same order of magnitude. If you want theta to be much smaller, right, to observe really small stuff, then perhaps, right, light will not be a very good choice. You need something that has a wavelength smaller than light, than visible light. Okay, possible candidate, UV. Other possible candidate, X-ray. Other possible candidates, electrons. Okay, then you may ask, right, how come electron can also do this? I mean, electron is a particle, right? We are using wave to see things, right? Or you're using light, all these things. How come you can use electron? That is quantum physics already. You cover it 2 topics, 3 topics down the road. It's telling you, right, that even things like electrons, right, the very, very small objects, they actually have a wave-like behavior within them. They can behave like a wave, yeah, and hence, right, there will be a wavelength associated with electron. So the electron, right, have a wavelength, and that wavelength, right, turns out to be really small. It's around 10 to the power of minus 10, 10 to the power of minus 11 meter. So you see, it is like 4 times smaller. It's 4 order of magnitude smaller than visible light. That means, right, that the theta minimum that the electron wave, right, can resolve will be like 4 times, 4 times, keep saying 4 times, 4 order of magnitude smaller. Yeah. Light can only allow you to see around 10 to the power of minus 6 meter, which is the size of a cell. But if you want to see the size of an atom, right, light cannot already, because light is the wavelength of light is way too big. Okay. So here I just what I just say is just for your info. Okay, you not exactly for your info lah. In when it comes to quantum physics, right, you may be asked, okay, why are electron microscope used to study atoms instead of using a light microscope? And that would be the reason that you give. Okay, so here you can see, right, the very small things under the electron microscope. The resolution is super good. You can see a lot of details on. This cannot be done with a light microscope. The bottom diagram, right, is a tunneling electron microscope. Above one is a scanning electron microscope. Bottom is tunneling. It allows you to see, right, at the atomic level, all these dots, right, are actually atoms on the surface of a material. So that is how fine you can see. Okay. Without further ado, right, let's just do one example. You may read the story here. So resolving power of the eye determined by blah, 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 blah. So different from just now that question, right? You see, instead of moving the object away, and we know the what do we know here? I forgot already. Let me read also. Okay. Got it. So we have the 2 lines, right, drawn on the paper. This paper was moved further and further, just like just now. Okay. But this time now, right, we actually don't know what is the size of the pupil. Okay, the aperture of the eye. Yeah. So, but we know, right, that when it moves until 5 meters, and the 2 lines are 2 mm, and this diagram is not to scale lah. 2 lines are 2 mm apart, and move until 5 meters. So we know this is the limit. Why that? Because, right, that's what the experiment is about. It moves until this far, then cannot see. So now this theta is not determined by calculation. It's determined by the experiment. You move until cannot see. Move until cannot see, right? That is at 5 meters. So you can calculate 2 mm divided by 5 meters. Okay, will be equals to the theta. So that will give you particle theta. Then right, you use back the Rayleigh criterion formula, lambda over b. Okay, then you can find what is the b. Yep. Oh, so you see, this kind of problem, I always got two sides to the equation. One side will be the physical setup. Okay, how far are the two objects from each other? How far is that two objects from the viewer? Okay, so this will form a ratio. Okay, the opposite over the adjacent side. Yeah. Then on the other side of the equation will be the lambda over b. If you have done a few times of this, right, you'll be quite familiar. People who always feel that this one is very difficult is because, right, maybe not enough practice also. Yeah. You do one or two times, right, you know what those terms mean, and you get a feel of the pattern of this question, right? It's okay already. Okay, so let's go on. The second half of today, right, will be on standing wave. Okay, and let's just look at the introduction, right? How to standing wave form. So this line, right, is actually very generic, and it's actually yet, right, it tells you all the conditions for standing wave to be formed. So you want waves, right, which are very similar. Okay, don't say identical. This one is a bit too critical, but as a theory, right, as an ideal, of course. Same amplitude, frequency, and speed. Okay, usually, right, if you're talking about the same wave type, right, okay, then most of these are already fulfilled. The only thing that could be tricky to know is amplitude. Okay, because, right, due to different kind of setup, you have two waves, right? Usually, how does the wave come? How come for two waves? You could have two sources producing wave, blasting wave at each other. But then, right, at different positions, right, the two waves may have different amplitude. So they don't actually give rise to a full cancellation when they undergo disruptive interference. Yeah. So the resultant wave, right, will not be a very nice standing wave, which is why, right, the definition give the condition as such must be identical. Yeah. But in questions, right, they may not be so. And there will be some situation that you know the two waves, right, have different amplitudes, and yet, right, you solve them as though it is a standing wave problem. Yeah. Let's look at the video. This one I don't want to explain too much. You do a video, right, you can appreciate it better. Hang on now. Let me see if you can hear the sound.
Blue wave traveling back in the opposite.
Can you hear the sound?
So I'll just slow this down while it's happening. So here we can see the first wave, part of the wave is just about to arrive at the boundary, and it reflects and inverts, and the reflected wave interferes with the incident wave that's still arriving at the boundary. And that interference.
Okay, I just pause here. You see, there are a few things happening here. One is the red color waveform, and the other one is the blue, and there's also the dots. The dots, right, are the real displacement. Okay, the red color waveform, right, is like what is supposed to be if wave were to continue without superposition happening, okay, to the incident one. The blue one is what the reflected one supposed to be, okay. So you can see, right, that number one, right, you see the red color waveform, right, when it hit the wall, automatically, right, the blue color one that comes out, right, will be opposite in displacement, okay. This is something that we call a switch, the flip of the phase angle. Every time you hit a hard surface, you undergo a phase change of 180 degrees. So, oh, sorry.
We're going to have that represented by a blue wave traveling back in the opposite direction. So I'll just slow this down while it's happening. So here we can see the first wave, part of the wave is just about to arrive at the boundary, and it reflects and inverts, and the reflected wave interferes with the incident wave that's still.
Yeah, I was saying, right, they will undergo a phase change of 180 degree. So whatever that goes into the wall, that hits the wall, right, it will, the reflected wave, right, that comes out will have a 180 degree phase difference. Yeah. So whatever that was there, reflected one is always its opposite. Therefore, right, when they superpose each other, or if I'm X, the reflected wave come out will be a displacement of minus X. So result always 0, okay, on a hard surface. Yeah. And hard, I don't mean, right, there must be a real surface there. Because, right, later on you'll study some situations, right, wave can even reflect when there is no reflecting surface per se, or physical reflecting surface.
We're going to have that represented by a blue wave traveling back in the opposite direction. So I'll just slow this down while it's happening.
Sorry,
So here we can see the first wave,
just cannot toggle to the part on the show.
Boundary, and it reflects.
I just watch it
and inverts,
slowly.
And the reflected wave interferes with the incident wave that's still arriving at the boundary. And that interference results in a kind of cancellation of parts of the wave, so they're interfering as per the principle of superposition. And
so the black dots, right, you see, no longer follow the red line, also don't follow the blue line. It follows the
what we
resultant.
can see is as the returning wave, the reflected wave, interferes with the incident wave, we have the conditions required for a standing wave to be set up. And you can see that we get this pattern of stationary nodes and antinodes along the wave. And we have a standing wave, which is this black wave, which is just the superposition of the two waves of equal amplitude and equal frequency traveling in opposite directions. And because of the phase change that happens at the boundary, we always end up with a node at the fixed boundary. So that's a boundary condition for a standing wave on a string. If we have a fixed boundary, the two waves will always interfere destructively there.
Hello, in this short video.
This one I think we'll skip. Okay.
Hello, in this short.
So let's look at what happens, right, to the kind of standing wave that may be formed in a string. Okay. And here we have one string, right, that is attached to both ends. Okay, two sides which are fixed. What's happening at the fixed end, right, is behaving like what I say is a hard surface for the wave to be reflected. Okay, so wave, when they reflect off a hard surface, always undergo phase change. Wherever that goes in, come out will be opposite of itself. So the superposition of these two incident and reflected wave, right, always result in a total cancellation. So where the ends of the strings are, you'll always have a node. Okay, a node is the positions that you find no displacement. Yeah. So you know the ends must be nodes, and this is also called the boundary condition. We'll talk more about it later on. So for the fundamental mode of vibration, right, you look like this. These two places, right, the two ends are forced to be not moving. In between, you can do anything you like. Turns out, right, that the middle will be exactly the place whereby you get the greatest amplitude. Okay, so this entire mode of vibration, right, is called the fundamental mode of vibration, or the fundamental frequency of vibration. You always draw out this thing, then you start to relate to the setup. If the distance of the two fixed ends, right, to each other is called L, then, right, the wavelength will be equal to 2L. Okay, how do you see so? Because, right, you see, this is just half the wavelength. To see the full wavelength, you have to draw out on the other side. Yeah. So the full wavelength, right, will be 2 times of L. Okay. Then right, you go on and write the frequency in terms of the L. Okay, in terms of the wavelength. Sorry. So frequency is equals to V divided by wavelength. So V divided by 2L. So you have half V over L. I purposely write out the half in front for a reason. Okay. Similarly, right, what about the other modes of vibration that can take place? The only thing that can that restricts the standing wave, right, is at the corner must be nodes. In between, you can do whatever you want. But what does whatever I want mean? Well, you see that there's actually very little choices that you have. You can fit more of the like a half wavelength thingy, okay, into the space in between. So now, right, instead of having one of the half wavelength thingy, right, being fitted in, you can now fit 2, or you can fit 3, and so on. That's what it means by you can fit whatever you want inside. Yeah. So you do up the math, right? Turns out that this one is equals to V over L, or actually, right, this is equals 2 over 2 V over L. Then the third one, right, will be 3 over 2 V over L. Okay. So you can see, right, that this one, right, actually has a relation to the first one. This is equals to 2 times, hang on, mouse is not working too well. I can't write too well here. So this is 2 times of F, of F1. Yeah, then the third one will be 3 times of F1. And you can start to see the pattern. You'll simply be right, N times of F1. Yeah. So this word, right, harmonic, is referring to, right, the multiples of the fundamental frequency. So if F2 is equal to 2 times of F1, then you call F2, right, the second harmonic. Okay. You may think that this is very obvious, right? Why do we need to say that that is a second harmonic? We already see that it's very obvious, right? The second one will be second harmonic. When you look at later cases, right, you realize that that is actually not true for different kind of scenario. Okay, but for this one, that is just it. So it means, right, that a guitar string, for example, which is fixed at 2 ends, right, is capable, when it's vibrating, is capable of producing, right, F1. And at the same time, right, it is also vibrating somewhat in F2, somewhat in F3. Okay. And you will have those frequencies of sounds, right, corresponding to 2 times F1, 3 times F1, all appearing and mix up together. So when you plug a guitar string, right, ding, it's actually not one frequency. You hear dominantly one frequency, which is F1. But right, mixed within the F1, right, also got F2 and F3. So all these subsequent higher frequencies, right, for the guitar string will be like you never skip any integer multiple. So it will be 2 times, 3 times, 4 times, so on. They all exist in the same string. Okay, but most of the energy, right, is within the fundamental mode. Okay, that's what all these things mean. Yeah, so this is we mentioned this just now already. Forgot about this. Now, right, let's look at air column, which is the slightly more difficult case. Guitar string is easy, no? Wave in a string is typically easier to understand because you can also see, right, the animation, right, that shows the up and down. Just on those animations, right, are showing strings. But for air, right, it's very tricky already. Wave in a string is transverse, so you can see it very easily. For air, we are talking about sound wave, and sound wave are longitudinal. So the vibration, right, is along the wave propagation direction. So it's harder to visualize that because they are along the same line. For transverse, it's easy because in a forward direction will be the wave, but then the displacement of the particle will be up and down. Yeah, so you can see it, right, very clearly in a two-dimensional diagram. But longitudinal is harder. So we have actually two conditions here. At the position where you have a wall, okay, there will be a hard surface. So hard surface reflection, right, will always be such that there'll be a phase change of 180 degrees. So resultant displacement always will be 0. Okay, nothing will happen there. You think from the point of view of a air molecule. Air molecule are supposed to be vibrating, right, in the sound wave. Cannot vibrate because it keep on knocking into the wall. So the air molecule that is like around the region of the closed end cannot vibrate. But want to vibrate, hit the wall. Also, you say, okay, forget it. I just do nothing. Then who can vibrate a lot? The guy that's at the open end. Because no restriction, is you go out, you see the big open world already. So it can vibrate most vigorously, excited. And what happened to the guys in between? Up to you. Can be anything really. Yeah, by anything, right? We're referring to like that. So you can fit whatever you want, okay, subjected to the boundary condition. So the first thing that you can fit, right, is to fit 1/4 of a waveform inside, because, right, at the open end, it must be an antinode, closed end must be a node. You can fit 1/4 of a waveform. So you get the first set of equation. Second one, you can fit 3/4 of a waveform. Third one, you can fit 5/4 of a waveform. And you can start to see the pattern, okay? Because of the fact that, right, one end is closed, one end is open, right? It always, right, force you to have another like 1/4 of a waveform like at the end like that, okay? So therefore, right, all of these will have a 1/4 of a waveform hanging outside, okay? Yeah, you see, here's like a quarter. Here's like a quarter. Then here is like a what? Here's like a half. Here's like a 2 halves. Here's like a 0 half. So that's the pattern. So you write out, right, it will be 4L. And 4L, right, is actually equals to hang on now. No. Not that. We'll look at the relationship will be more obvious in the F part. So F, right, will be 1/4 V over L. Then F2 3/4, F3 5/4. So you can see, right, this is equals to 3 times of. I can't write 3. The mouse can't allow me to write 3. I'm so sorry. 3 times of F1. And this is 5 times of F1. Can't write. I give up. Okay. So yeah, you can see, right. Therefore, right, we call the second one third harmonic, third one fifth harmonic. Got 2 and 4, don't have. So if you play an instrument, right, that works on the principle of a closed pipe, right, most the main sound that you hear belong to the fundamental mode. Okay, that one no issue. Always a case one. Then, right, you wouldn't hear any sound that is twice that fundamental frequency, but you'll hear the third. You won't hear fourth, but you hear the fifth. Okay, something like that. Then for the open pipe, it will be something like this. Okay, the condition is antinode at both ends. You can do whatever you want. So the first case of do whatever you want, right, is just to crisscross in this way. So essentially, right, the whole length will just be equals to half of the wavelength. So first wavelength is equals to 2L. Second one, you see, you can subjected to the boundary condition, you can do whatever you want. So you can fit half a wavelength inside, and 2/4 of a wavelength overhanging. Yeah. So see, this is once again, right, a quarter, and here is another quarter. Okay. Then here is also a quarter, and the other side is also a quarter, but in between you can fit another half. So third one, quarter and quarter and 2 half, and so on and so forth. So here you have the equations. This one is similar to the string. you can see that it has a second and third or 3 times of the fundamental. Yeah. So to summarize, right, these are the equations. Do you need to memorize? Never. If you ask me, right, to write it out, I cannot one. I need to draw out. Then I relate. Then I arrive at the formula. Okay, and you don't need to memorize. You won't be tested in a way that need you to use the formula directly, but you'll be tested in a way that you need to draw to understand. Okay, so drawing, understanding, forming the relationship is the important skill, not about knowing the formula. Okay. Now, right, just one question, right? See, every time when we draw standing wave, we always draw this kind of dotted line, right? To show that there's a standing wave inside. But what do the dotted line mean? Okay. See, this is the top is the standing wave animation, right, for the particles. You can see, right, that on the top diagram, right, there are 2 red dots. Okay. So this guy here, right, is like always not doing anything. Whereas this guy here, right, is like moving left and right. Oh, so see, that guy corresponds to where? Here. And this guy corresponds to here. Then in between, right, these guys are like smaller amplitude, front and back, small amplitude. So these are like these guys. Therefore, right, this line that you draw, right, whenever you draw this kind of standing wave diagram, is referring to like their relative, the size of their amplitudes. Okay, so all these things are performing SHM, but it's not like they are stuck at one point or have a particular displacement at all the time. No, they are always moving one. The dotted line, right, is referring to their amplitude. What's the boundary of their motion? Yeah. So just that you know that what you're drawing. Here, right, comes a question. Which particles do you think are in phase with each other? Okay. You can think in your head, or I don't want to ask people for answer really. Nobody will answer me. So just tell you the answer. You see, if you look at A and B, just look at the way the waveform, right, swings up and down. You can see, right, that at A and B, right, is actually in phase one. C and D are also in phase with each other. But comparing A and B versus C and D, right, they are actually in antiphase. Yeah. And E, right, is actually in phase with A and B. So with this, right, we can actually come to a conclusion that anytime, right, that you have particles between 2 adjacent nodes, all the particles there, right, must be in phase. Also includes, right, like here, 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 any point, all these are in phase. Then when you go across a node to another side, right, then you will be in antiphase with them. Okay. So for standing wave, right, phase relationship is only 0 or 180. Don't have anything in between. Yeah. Here and nothing to say. Oh, he's talking about pressure. Okay. You see, consider this point that we have drawn, labeled in red, right? Oh, this is a displacement node, right? Not okay. This is a displacement node. This guy, right, not moving. But then you look at what are the people around him doing. Or at some moment, right, they are like going far from him, then sloshing towards him, squeezing him, or far from him, squeezing him, far from him, squeezing him. So see, far and squeezing him, right, means what? Means, right, the pressure will change. When people are far from the particle, right, or that is low pressure. Or when everyone come towards him, right, or high pressure. Yeah, don't you feel whenever you go to a gathering, right, a lot of people, you feel pressure. Or when you're by yourself, very peaceful. Okay. Yeah. So the point, right, that is not moving, actually, right, experience great pressure change. the pressure could go very low and could go very high. On the other hand, right, the guy, right, that is at the empty node, he's moving a lot, okay? But by and large, right, his location, like, although got 人来人往, okay, but right, the average pressure is like more or less always fixed one, okay? So where is empty node, right, for displacement is actually a node for pressure because very little fluctuation. That's what it means. So connection between pressure and displacement, node and node position is moved by 90 degrees. Or simply, right, just flip the relation. Node become anti-node become node. Anytime you forgot why this is the case, look back at this diagram, then you can appreciate already. Okay, in summary, right, this table tells you all the differences between standing and progressive wave. Standing wave do not advance and do not propagate energy. So you see these two are like very related. And here it says waveform. Waveform means the diagram lah. The diagram will move. A while later, you'll still be on the same spot, but it will look like different still, but the whole thing won't translate. Yeah. Amplitude different according to position. Whereas for progressive wave, right, that is like doesn't change amplitude, then you stay constant. Frequency is talking about the frequency of the SHM performed by the particles. So it's the same throughout. Everyone has the same frequency, except the particles at the node. They are not vibrating. So no frequency to talk about. Phase, we talked about it already. For progressive wave, particles one wavelength apart will be in phase. Otherwise, you use the formula. Yep, that's it. This example, right? Okay, let's start. I forgot to include the answer. Alternating loud and sound wave can be heard. Okay, I'll just narrate it out. Okay, because my mouse cannot write. Can be heard, right, as the person moves from speaker to wall. Explain why so. So this is where, right, this 套路of explaining standing wave will apply. You'll always say, first come out with, right, see how to form standing wave. Must have two wave, right? So you'll say what causes the two wave. Okay, so as a person, right, move towards the wall, there will be a wave coming directly from the loudspeaker, moving towards him from one direction, and there will be a wave coming, there will be a reflected wave off the wall coming towards him in the opposite direction. Okay, so that's number one. So you account for the fact that there are two waves moving in opposite direction. At certain positions, these two waves will have a phase difference of will be in phase. These two waves will be in phase and hence undergo constructive interference and leading to the man hearing the loud sound. At certain position, the two waves will undergo destructive interference, leading to the man hearing a soft sound. And this is why, right, as the man walks towards the wall, he will hear alternating loud and soft. Okay, so you first talk about origin of the two waves. How come got two waves? Isn't it only one speaker? No, it's speaker in one direction, reflected wave in the other direction. Yeah, then you talk about the condition for constructive and destructive interference. Then you round it up by saying, hence why as you walk towards the wall, you go through all these positions. Okay. Second, third part I'll skip. Okay, maybe I'll just send the solution later on. Yeah. So this one you must practice and try. Yep. For this one, this is yet another kind of problem that will always come out. Which position will loud sound be heard? Loud sound be heard means what? A lot of people know how to solve this problem, but they don't know what does loud sound mean. Loud sound means, right, that you see, here we have a sound source, which is a tuning fork. You strike it, give you a particular frequency. Then this frequency of sound, right, okay, have a particular wavelength. And right, it will interact with this air column, okay, within the tube. So if the standing wave, right, could be formed within the air column, right, then the energy go in, okay, through the form of a sound wave, cannot come out because, right, standing wave means what? Means, right, no energy is moving, okay. But then, right, there will be a source. So the source, right, like create disturbance. Then, right, the particles inside, right, the energy can't really propagate outwards, right? They form a standing wave. Energy don't really propagate outwards. They'll store and store and store. The particles, right, amplitude got larger and larger and larger. So in turn, right, this whole air column itself, right, behave like a new source. Yeah, behave like a new source. So the air column also give out sound, okay, wong 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 sounding, okay, and that's why, right, we hear a loud sound. It is like collect the energy from the tuning fork, or store, then become bigger. Then at some point, right, the amplitude of the vibrations inside all quite strong, okay, then you hear a loud sound. Yeah, so how do we work this out? Well, you see, refer to the wavelength on top. So 1 unit here is a quarter of a wavelength. So you will expect 1/4 here, 3/4 here, 5/4 here. Okay, then you draw in the wavelength, the waveform. So you'll just be like that. Oh, the mouse weird. Sometimes work, sometimes don't work. Yeah, don't want to draw already. Don't want to try my luck. Okay, the mouse I think will give me problems soon. Lastly, right, something called the end correction. End correction, right, is this phenomenon whereby, right, the standing wave actually overreach or past the length of the tube. Okay, it pop up by a bit. Why will this happen? Because, right, how will the air molecule know where's the end? It only agar what? It knows that, oh, like outside is slightly more free, or inside very stifling. But where is exactly is the boundary? Also don't know. Okay, so the air molecules, right, will somehow overstep the boundary by a bit. Okay, so the antinode appears actually outside. Okay, not yeah. So, and how do we go about doing this if the antinode is actually outside? Because it's no longer equals to the length of the, you can relate directly to the length of the pipe. Okay, so that is where, right, we do this correction called end correction. So in the first case, right, you see lambda over 4, right, is equals to a bit more than the length. Okay, so it's length plus the correction. And the aim of problems surrounding end correction, right, is always to form an equation like this. Okay, then, right, you will always have multiple set of scenario. The first time you get the resonance is at this length, the second time is at another length. Then you have more than one equation that you can form, and each of these are talking about the same pipe. So the end correction, right, could be assumed to be the same. So you have multiple equations containing the same plus C. So then now you know, okay, if I subtract the equation with each other, then the C will disappear. So that's how you can still solve without knowing the end correction. It's actually an unknown. Oops. Yeah. So this example, right, is illustrate this end correction idea. So first part, you see you have two resonant lengths, right, by the tube. Okay, 30 and 96. So you know, right, 30 is not 1/4 the wavelength. 96 is not 3/4 the wavelength, but it's 30 plus C is 1/4. 96 plus C is 3/4. Okay, then you subtract these two equations. So you know half a wavelength will be 96 minus 30. Yeah. Then you can find whatever you need to find. Now, if you need to know the end correction, then you substitute lah, because you now already know whatever that you know enough already, yeah, about the wave. So substitute it into either equation, because earlier we don't know what is the speed, or we don't know what is the lambda. So now we know what is the lambda. You can substitute back into either equation and we can solve. Okay. Lastly, right, give you one example to try. Okay, this is not easy. Most of the time, right, our problems are to do with changing the length. Okay, maybe move the piston of the tube. Okay, or let the water drain out at the bottom. Then you change the length of the air column, while keeping the frequency of the source constant, thereby wavelength constant. But here, right, we do a different manipulation. Instead of the length becoming different with the same wave, now we are changing the wave and keeping the length the same. Okay, so you can go and try and see whether you get the correct answer. Maybe I'll post it later on in the WhatsApp group. Oh, and finish. Any question? Any question for anyone? Anyone solve the last problem already? You want to share your solution? How, Katin?
Little Indian Station.
Little Indian Station.
Mr. Quack,
Yeah.
can you how to explain the which water is the loudest question again?
Okay, okay. This one. So what do you want me to explain? Is it why you will hear a loud sound, or why the positions are as such?
Like why the sound will be louder when it's like that?
Okay. It's because, right, that when you see, when the air column, right, can is the length of the air column, right, is suitable for standing wave to be formed. Then, right, standing wave means the energy is like being trapped, because energy don't move. Yeah. So, but yet, right, there's an external source, which is the tuning fork, and the vibrations from the air outside the pipe cause the air inside the pipe to vibrate. So energy, right, like enters, but then you form a standing wave. So once the standing wave is being formed, right, the energy don't leave. Okay. So the amplitude of vibrations, right, of the particles within the pipe gets larger and larger and larger. And it sounds as though it's like a source by itself. Okay. And in contrast, right, what about at other levels whereby you don't get standing wave? Okay, why don't you hear loud sound? At the non-standing wave levels, right, then because it is not a standing wave condition, standing wave won't be formed. So energy goes in and goes out, okay, without being trapped. So the molecules inside the pipe, right, won't accumulate bigger and bigger amplitude, okay. Therefore, right, there will just be no particular or no remarkable thing happening, okay. It will just be as though the same as with in any other direction. Another way of thinking about it, right, is how you can think about the whole air column, right, as a vibrating object. Okay, the whole air column as a vibrating object. In the sense of SHM. Okay, for example, right, SHM, you can think about a ruler, right, or don't say a ruler, pendulum. Yeah, a pendulum. Pendulum have a natural frequency, right? Or it's a vibrating object. Yeah, don't say vibrating, oscillating object. So you can think of the entire air column, right, as possessing a fundamental, a natural frequency. The air column is supposed to be, can also vibrate as one. Then which air column, right, will react to the sound? It will be those air column, right, with the same, with a natural frequency equal to the natural frequency of the tuning fork. That will vibrate. Because the tuning fork is now like the driver, and the whole air column is like the driven. Okay, so when the driver's frequency equals to the natural frequency, you have resonance. That's another way to think about it. And when something is resonating, right, it means that its amplitude is very large. Okay, therefore, right, it can produce significant disturbance to its surrounding. Okay, for this case, the entire air column's vibration is very strong. Therefore, right, it can disturb the surrounding air molecule to vibrate, and we hear it. All these are actually not essential to being able to competently solve this problem. These are just extra interpretations, good to have. Because it sounds complicated, right? Because it's really not easy to explain this phenomenon. To calculate is easy. Any other question?
Mr. Greg, so which one is the louder sound?
Oh, which one is the loudest sound? Or you mean that just now that question? The question is not asking for which one is the loudest. They're asking for where can you hear loud sound. Because at the bottom, right, you let water out, so you imagine at first the water is filled to the brim, so the water will run out, run out, run out. So the water level drop until certain level, you hear loud sound. Then as the water fall past that level, then the sound becomes soft again. Then reach the next suitable level, you hear a loud sound. Then after that, soft again. So if a question would be to be set about this, right, and water is like running out at a constant rate, or maybe they tell you water is running out at a constant rate, describe what the person hear, or then this person will hear constant fluctuation in loudness at regular interval, something like that.
Oh, okay.
But we don't need to compare which one is louder. I also don't know. Any other question? If not, take care and have a safe time in school. Okay. See you guys soon. Thank you.
Thank you, Mr. Craig.
Thank you, Mr. Craig.
Thank you, Mr. Craig.
Thanks, Mr. Kurt.
Thank you.